We have a free neutron that undergoes beta decay, forming a proton and an electron. If I have a neutron, it doesn't have any charge. It has a mass of 1. And they say it's going to undergo beta decay, which would give us a negative charge on the electron and no mass. And it would also form a proton. So I'll go ahead and write it as a proton that has a charge of +1 and a mass of 1. And you can see that, 1 equals 0 plus 1 and 0 equals -1 plus 1. Makes perfect sense. They want to know how much energy is released in this nuclear reaction. And then once we figured it out, they want it in kilojoules per mole. This thing has been pulled apart. This is a binding energy problem. So binding energy comes from what? It comes from the mass deficit. So I need to figure out what the masses are here. The neutron, if I go look up the neutron, I find out that its mass is 1.67493. I really do need all of these sig figs for this problem. Times 10 to the negative 27 kilograms. So that's this side. Over here I have an electron and a proton. Well, I'll start with the proton and I'll write down what it is. 1.67262 times 10 to the negative 27. And I need to add to that the electron. It's not the same exponent here, but your calculator can do this problem for you. So once you enter those two into your calculator and you add them together, you're going to get 1.67353 times 10 to the negative 27. So what is the mass deficit here? I am going to subtract. This one's bigger than that one. Okay, so I will subtract this from that. 1.67353 times 10 to the negative 27 kilograms. Subtract. Let my calculator do it, although I will write it down this way to begin with, just so you can see since they're both negative 27, I can do that. Your calculator would tell you 1.40 times 10 to the negative 30 kilograms. That's my mass deficit or mass defect. Yeah, okay. What's the binding energy then? The binding energy is this delta M and then the speed of light squared. All right, 1.40 times 10 to the negative 30 kilograms. And the speed of light squared, well, I had a lot of sig figs before, so I'll go ahead and use a few more than I normally would here, and that's squared. And then I have to use the calculator. I'm going to round back to 3 sig figs on this. Negative 13. Now, kilograms, meters squared per second squared is going to be joules. This is per neutron because we did this for just one neutron. So just one of them will have this happen. This looks like a very small amount. But they didn't want it in this form. They said they wanted the answer in kilojoules per mole. So, okay, I need this answer in kilojoules per mole. And I'm starting with it in joules per a single neutron. So the first thing I'm going to do is say I really need my moles here. So there would be 6.02 times 10 to the 23rd neutrons in a mole. And then the last thing, I want it in kilojoules. So 1 kilojoule is the same thing as 1,000 joules. And that will take care of it. And I'll have my correct units. I will get 7.57 times 10 to the 7th kilojoules per mole. Whoa. So this is like 75 million kilojoules per mole. Well, let's round it up, 76 million kilojoules per mole. And we can compare that to something in a bonding energy, maybe 300 kilojoules per mole for a chemical bond energy. So now we can understand why everybody gets all excited and says we should use nuclear energy. Look at the difference here. It's 2 times 10 to the 5th more energy coming out of this.